This video will be learning to do calculations with photon energies and wavelengths, going one direction or the other. If you're given the energy, figure out the wavelength. If you're given the wavelength, figure out the energy. This is all going to be based on Einstein's famous equation. This is his other famous equation that you might not have heard of. It's one that relates the energy of a photon to its wavelength, and it's hc over lambda. Hc is a combination of units. H stands for the Planck constant, and c is the speed of light. Einstein figured out that there's a relation between those two constants and the wavelength of something and the energy of something. The units of Hc are going to be eV, that stands for electron volts, nanometers. And eV is a very small unit of energy, but it's one that's appropriate when you're dealing at the atomic energy level. A nanometer, of course, is a unit of length, a very short unit of length, but it's one that's handy for measuring light wavelengths in. So that's why we'll use it here. Hc can be expressed in many different combinations of units, but these will be the ones that are useful for us. Now, with a couple steps of algebra, you can solve Einstein's famous equation for the wavelength of a photon, given its energy, and we'll also do some examples with that. These horizontal lines represent the energy levels in an atom for an electron in that atom. And this is probably the best way to picture an atom, is just thinking of it in terms of those energy levels. The little red dot here can represent an electron, and right now it's in a state that's well above the bottom level. So the bottom level is often called the ground state of the electron. That's the lowest energy state that it can be in. The electron may vanish from that upper level and show up in a different level of energy. This is not necessarily a translation in space, and so try not to think of it that way. This is just a translation in energy. It'll also simultaneously undergo some changes to the way that it behaves, but don't try to think of the electron as a little tiny dot. Turns out that's an incorrect interpretation of it. It's much weirder than that, but it does have these energy levels that are well defined. Let's look at that transition in another way, though, and we'll think of the energy that is lost by the electron, represented by the length of an arrow that drops down here. And the lost energy shows up as a photon, which is the wavy yellow line here. And I'll go through that again. The electron loses energy. That lost energy shows up in the energy of a photon that is carried away or carries itself away from the atom. The difference in energy between the two levels we'll call E, and that difference in energy determines the wavelength of the photon. First, we'll calculate the energy range for visible light. And for visible light, the wavelengths range from 400 nanometers to 700 nanometers. 400 is the violet end of the spectrum, 700 nanometers is the red end of the spectrum. And we'll use just the standard version of Einstein's equation, the E equals 1. And we'll do the red light first, because the red light will have the lesser energy. The longer the wavelength of the light, the less energy the photons will have. So E equals 1240 electron volt nanometers, that's the Hc part, divided by 700 nanometers. The nanometers will divide out, and we'll get 1.8 electron volts. That's the low end of the energies for visible light. For violet light, lambda equals 400 nanometers. It'll be just like the last calculation, but we'll stick in 400 nanometers instead. Same numerator, 1240 electron volt nanometers. That's the constant, the Hc, divided by 400 nanometers. The nanometers will divide out, and we get 3.1 electron volts. The energies for visible light photons range from 1.8 electron volts for red light to 3.1 electron volts for violet light. Time for you to practice. The answers for these will be at the end of the video. Question 1. A spectral line in helium has a wavelength of 447.1 nanometers. What is the energy of this spectral line? You may wonder, what in the world is a spectral line? It turns out it's due to the way that we look at the light that atoms give off. We use a diffraction grating. That diffraction grating splits the light apart, and we also often use a device called a spectroscope. And when we do that, we see the different colors as distinct vertical lines. And that's why they're called spectral lines. The atom is going to be giving off light in every direction, and usually you see a mixture of it. But when you run it through this particular instrument using a diffraction grating, you see these vertical lines. So they've been called spectral lines ever since those things started being looked at in the 1800s. Second question. I'm just going to run through the 3 questions. You should pause the playback and do each of these on your own. So, wavelength of 504.7 nanometers, what is its energy? And a wavelength spectral line in carbon with a wavelength of 165.7 nanometers. Now, this is not visible. It's well below the 400 nanometer kind of approximate bottom limit for visible light. People aren't going to be able to see this, but we still call them spectral lines. So what's the energy of that one? All right, pause your playback, do those problems. I'm going to move on. Now we'll go the other direction. We'll get the wavelengths from the energy differences, or the energy of the photons. On the right side of the screen here, I have the energy levels for hydrogen. These aren't exact. I don't have a lot of significant figures on these, but there are much more precise measurements of these things than what I've got on here. And we're going to start with Einstein's equation, but 2 steps of algebra will get you to lambda equals hc over E, and that's what we'll be using here. Now, for the first thing we'll consider, think about that 10.20 electron volt transition that could happen if an electron was initially in the 10.20 eV level and dropped down to that 0 level. That 0 level is called the ground state, by the way. Sometimes you see these numbered in a different way. They'll start with 0 up at 13.6 electron volts and apply negative numbers to everything below that, but the differences will be the same. Anyway, that's what we'll do. So a 10.20 electron volt transition, the wavelength will be 1,240 electron volt nanometers. Again, you'll probably have that memorized by the time you get done with these, divided by 10.20 electron volts. In this case, the electron volts divide out, and you'll be left with nanometers, which is the appropriate unit for wavelengths here. And we would get 122 nanometers. Now, that's not visible. That's down there in the ultraviolet part of the spectrum because it's below violet in wavelength. If we try another transition that drops down to the 0.00 level, from the 12.10 electron volt down to the 0 level, then the photon energy will be 12.10 electron volts. So lambda equals 1,240 electron volt nanometers divided by 12.10 electron volts. Again, the electron volts divide out and we'll be left with nanometers. And we get 103 nanometers. We're moving farther away from the visible part of the spectrum. And that's not surprising. This is an even more energetic transition than the other one. Now, if you think about it, there will be no transitions down to that zero level in hydrogen that produce visible light, because all the rest of the energy levels are above the ones that we've calculated, so there'll be even larger numbers and they'll yield even shorter wavelengths. By the way, there are actually many more energy levels than this. In between the top level and the level just below it, 13.22 electron volts, there are an infinite number of possible energy levels. I didn't bother to draw them, and I didn't bother to put numbers on them either, because it was hard enough to make this diagram. None of the transitions to the 0.00 level in hydrogen produce visible light. They all produce ultraviolet light. So let's consider some other possible transitions. For visible light, the wavelengths go from 700 nanometers with an energy of 1.8 electron volts to 400 nanometers with an energy of 3.1 electron volts. So visible light photons have energies between 1.8 electron volts and 3.1 electron volts. If you want to look for visible light, just look for energy differences between those levels that are between 1.8 and 3.1. And we're going to find all of them here, actually, for hydrogen. That's the important thing we need to remember. Visible light photons are between 1.8 and 3.1 electron volts. Now, let's consider that transition, 12.10 down to 10.2. The energy of the photon that would be given off is the difference between those two. It's 1.9 electron volts, and that is between 1.8 and 3.1, so that will be visible. It's a very pretty deep red color. Another transition, this one from 12.75 down to 10.20. We can calculate that difference, and you get 2.55 volts, electron volts. This is between those two numbers, and so this will be visible. This is a very pretty turquoise number. I think of it as turquoise anyway. Third transition, from the 13.06 down to the 10.20. That'll have an energy of 2.86 electron volts. So we're nearing the top of the energy scale for visible light, but that one would still be visible. That's quite a deep violet color. Then the last transition here that we'll look at, 13.22 down to 10.20. We can do the subtraction on that, and we get 3.02 electron volts. This is a very deep violet. I'm not sure that my eyes are actually sensitive to this. I've tried to see this before, and maybe I just didn't have a good enough instrument, or I wasn't in a dark enough place, but I haven't been able to see that one. There's another one that is just barely shorter than 400 nanometers in wavelength that should possibly be visible to some people, but I haven't been able to see that one either. Some of these transitions don't occur rapidly, and so they're not very bright lines anyway, but those are the four that we'll consider visible for the hydrogen atom. And so your extra practice is to look at each of those transitions, and here I've just given them letter numbers, which I just made up for this, so don't assume those are what they're called. But for each transition, calculate the wavelength and the photon produced, and I used much more precise values of the energy levels when I determined these energy differences. So these will be more precise, but transition A, 1.889 electron volts, B, you can see what they are there. So pause the playback here and go ahead and see if you can get answers for each of those. Keep track of the units while you're doing them. Write that 1240 electron volt nanometers with those units there and see how the units divide out. And that's an important part of it. The numbers mean nothing without the units. Okay, here are the answers to these. And if you got them all right, good job. If not, go back and check your calculations. I'm assuming here you know how to do those numbers on your calculator. In this case, it's just division. But go back and check your work if you didn't get them all correct.